recording. There we go. Of course, we were talking about, wait, what does this say? Encoding overloaded. Man, I think my computer's getting worse. I'm gonna try to close some stuff. Close. Poor computer. Part of me will close like Microsoft Word and all that crap. I guess I can close Visual Studio. I don't think we're going to be using it today. That'll probably save some resources. Okay. Here's hoping the recording is doing fine now. All right. So, talking about the binary search trees. And we saw how, I mean, really the huge advantage we're seeing so far is that we can search through this list, or this list, the binary search tree to see if something's in it very quickly, very efficiently compared to like a regular old tree or a linear search. Because we can do what we call like a binary search with the binary search tree. What we did yesterday was the binary search. You make a question and then you make one of two decisions. And by doing it, you get to throw away roughly half the stuff. Half the stuff minus one because the question you asked counts. So that's fantastic. And really, sure, they're a slightly more sophisticated data structure. They've got more specialization compared to the regular tree, but they're not that much harder to implement really, because all we have, like when we add, all we have to do is make sure we add it in the right spot. But the algorithm to do that is basically the binary search algorithm, which is basically the same as the search algorithm. It's just instead of searching both sides, you will only ever search one side. So we get a lot more like power, for lack of a better term, with such a simple little addition. It's wonderful. Now, of course, maybe you've got some data you want to store in your tree that doesn't really have a particular ordering, you know? So I guess that doesn't really make sense for a binary search tree. Or maybe not all the areas you're using it makes sense to have even a binary tree. And that's fine. Like we can have general trees. But if we can use a binary tree, there are some advantages there. And when I say things like that don't have an ordering, like what I mean by that is, like think of the cells in assignment 2, not assignment 3, because in assignment, I mean, you could think of them in assignment 3 too, but the cells in the maze themselves didn't have an ordering. Sure, I know in assignment 3, you used the priority calculation with the A* calculation to give the cells an ordering, but the cells themselves didn't really have an ordering. The cells are just cells, you know? And if you're having a hard time understanding what I mean, really just think assignment 2. The cells are they're just there. Like if I gave you 2 arbitrary cells and I say, what comes first? You're gonna go, what? That question doesn't make sense. If I give you the color blue and the color green, if I gave you 2 pieces of paper, the color blue and the color green, and I ask you, what comes first? Chances are, unless you go to like, well, wavelength values, chances are you're gonna go, what? That doesn't really make sense. Because these things, I guess wavelengths, we could count that as the ordering. Maybe I could pick another example. If I gave you 2 rocks, which one comes first? You're going to say, well, like, do you want me to sort them? Like smaller, heavier, matte? Like, what do you want me to do? So some things don't have this like obvious ordering, or sometimes we have to define the ordering for these things, which we have talked about. But when we're playing with numbers, well, whatever, they've got their orderings, right? Integers, we know 1 comes before 4 and 4 comes after 3 and so on. Anyways, let's continue. So we basically talked about, so what did we finish? We talked about remove the min, remove the max, find the min, and the adds. But we avoided like, we avoided some of the arbitrary removes and whatnot because it can get complicated. And those are the things that are outside the scope of this class. You'll learn that in 255 next year. And we talked about the traversals, which are the same for a binary search tree as they are a regular binary tree. But the cool thing is the in-order traversal will actually give us the numbers in order, which is kind of neat. So what else would we want to add? A whole bunch of stuff, but that's for next year. Let's not worry about that. Okay. So we just learned about these binary search trees. And not too long ago, we learned about an ordered list. In fact, you all learned about a priority queue, which is kind of like an ordered list, right? So I'm wondering if we can somehow, like if I gave you a list and it's an ordered list, we could do a binary search on that, but we'd have to get fancy with whatever data structure we use to make the ordered list. What else? Like there's a lot of other things like an ordered list and this binary search tree kind of have in common. So for a moment, let's pretend we have a fully functional and working implementation of a binary search tree. We don't, okay? We didn't even talk about how to implement the removes and whatnot. But let's pretend for a moment we've got a fully working binary search tree. We have the add size is empty and it has the arbitrary removes, okay? So with an ordered list, we need to be able to do a couple of things. We need to be able to add things such that the ordering is preserved. We need to remove arbitrary things, get the size, and figure out if it's empty. So, I mean, we could talk about an array implementation of an ordered list, but let's talk about a linked implementation of an ordered list. So we have this ordered list, and what's the computational complexity of an add? So you're going to have to, unless you've got some fancy indexing, and I don't know how you're going to do it, you're going to have to do like a linear search through here to find the place where you need to add the thing, right? So if you're adding like 15 and this is 1, 7, 14, you're gonna have to go down and find where it belongs, and it should go between these two. Wait, I said 1, 4, whatever. I think it would go here based on what I just said, but maybe I forgot. And what's the computational complexity of a remove? Well, you're gonna have to do the search for it in this linear data structure. So, we're thinking order n. If this is a linked implementation, if we have an array implementation, maybe we can get a little fancier, but let's talk linked implementation. So we've got this add and remove, and they're linear. I mean, even if we did a search through here, it's gonna be linear, right? I mean, sure, you might say, well, you can stop the search once you find a number that's bigger than the number you're looking for, which is true, but for all you know, if this list has 1, 2, 3, 4 in it, and I'm searching for the number 99, I'm gonna have to go all the way to the end. So there's a lot of linear operations here. So remember though, with the binary search tree, the search for an element is not linear, it's log n. And the complexity to add something, it's not linear, it's log n. And the complexity to remove something is also going to be log n, as opposed to linear. So suddenly, if we actually use a binary search tree data structure as the container for our ordered list data structure, we get way faster and better searches, adds, and removes. So by using this clever data structure, which in itself is a data structure, we can build a fancier version of another data structure, the linked ordered list. And that, to me, that's awesome, right? So that said, we actually do have some drawbacks because, and maybe we can think about an implementation where in our ordered list, we don't just have a pointer to the head, but maybe we have a pointer to the last one too, kind of like a queue. So we could do that, I guess, right? And if that's the case, remove first would be order 1, and remove last would be order 1 as well if we had a pointer to the last one. Otherwise, it's linear because we have to get to the end. And we will actually go from this constant time look to a log base 2n one. So this actually gets worse, and this would get worse too if we had a pointer to the end. And remove though, the general remove will go from linear, something that's guaranteed to be linear, to log n, which is fantastic. And same with first and last, we'd lose something there, but asking if something is contained within it, we don't have to do a linear search anymore. We can do the binary search with the binary search tree. Is empty and size are basically the same, and add also goes from linear to log base 2n. But there is an asterisk here, and this is what we talked about last time, very briefly at the very end of lecture yesterday. But the point here is, we get some serious improvements, but we also get some drawbacks. And you might be thinking, well, but what's then what's the right choice? You know, sure, I go from linear to logarithmic, but I'm also going from constant to logarithmic, which is bad. So how do I know which one to pick? And well, maybe it's a problem specific. Maybe you're going to be adding a lot of things to the front and removing a lot of things from the front of your ordered list. And if that's the case, then maybe you should stick with the linked implementation. But if you're going to be doing a lot of middle of the road arbitrary adds and removes, well, maybe the binary tree implementation has a better computational complexity for your use. Or I guess not. It'll have a more desirable one for what you're going to be using more. I guess I could actually go to full screen, eh? No. What? There. Okay. Now, we did talk about this very briefly yesterday, but a balanced tree has the property basically that the leaves are all on the same level, but they can be off by one level. But it's not like one level either way. It's like in one direction. If there's another level, then everything that's extra must be in that level. What I mean is, if you had something like this, we're in trouble because this has, like, the difference now is that. And the thing is, the height of the left and right subtrees can differ by at most one. Oh wait, no, I guess maybe this is fine because the height of this subtree, maybe it is fine. No, I don't think so. Whatever, maybe I'm getting confused with my implementation. Not too much of a deal for the point we're making though. This is not balanced. Which of these is balanced? Well, I spoiled it, this one. So if I wanted to create a tree, if we did this and we're building a tree and I say add, okay, that happens. 5, let's add 5. Well, 5 is bigger than 3, so it goes to the right. 9's bigger than 5, so we add it to the right subtree. 12's bigger than 9, so we add it to the right subtree. 18's bigger than 12, so we add it to the right subtree. And 20, well, that's bigger than 18, so we add it to the right subtree. This is what we would call a very unbalanced tree. It's a degenerate tree. And the reason is, well, you know, typically we like our trees to have a height that is like log of the number of nodes. Like it's got this log relationship. This is an H for height, not an N. Or vice versa, an exponential height. So that's that way. And then height has like the 2 to the n relationship, or height relationship. My goodness, I'm all over the place. Whatever. Point being, if you wanted to do a binary search, you're not getting a binary search. This is a list. This is effectively a list. Although there are a whole bunch of pointers to left children that don't exist. If I'm looking for the number 21, well, what am I going to have to look for? Or let's say 23. What am I going to have to look at? Well, 23 is bigger than this, 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 and see if it's there. I'm going to have to look at all n things. I don't get to throw away half the trees like I did. And this is a degenerate tree. It's basically a linked list. And don't get me wrong, this is an extreme case. If we had something that looks like this is still problematic. And even here, and something like that. Like this is not good. This is bad because all of the power we get from the binary search tree really depends on the tree being reasonably balanced. So we don't like this. This is bad. So the worst case time complexity, well, that's order n. So if it's balanced, it's log n. If it's not, it's order n. So if our tree's not balanced, we could be doing linear operations on something that we're hoping to get logarithmic computational complexity on. Now, there are some really cool strategies that will automatically address this issue. So there's things called like red-black trees and AVL trees. These are well outside the scope of this class. This is stuff you're going to learn about next year. And you might actually only learn about one of these two, probably AVL, but maybe I have it backwards. I am partial to AVL myself because I think they make more sense. But basically, whenever you add something or remove something, it does it in such a way that it ensures that the tree has these like the balanced property, and it does things called like rotations if we have the AVL trees. And so they're self-balancing, so it's a nice, a little bit of upfront extra computation cost, but it's all like mostly constant time stuff. And then you get way faster, like you're guaranteed to have these logarithmic operations now, and you won't have these degenerate trees. So that's really cool. But again, well outside the scope of this course. There. So, are there any questions now about what we just learned about with the binary search trees? So, because yesterday we learned about binary search trees, and then today we kind of talked about how we can use the binary search tree as like a container for our regular old linear ordered list. And we get speed ups in some places, but you know, there are drawbacks in other places. So any questions about that, or are we all happy? Can we get the 60-second summary of a red-black tree? What happens if the tree isn't balanced? So it sounds neat. Red-black, I can never even remember the red-black tree. But I can see if, I'm gonna have a quick look on my computer, see if I have some actual nice slides that do the visualization for the AVL trees. And what happens if a tree isn't balanced? What do you mean? So like in an AVL tree, if it's not balanced, it'll do like the rotations to balance it. But if we're doing, like if the tree isn't balanced, it'll still work, but we'll lose the fact that like, well, binary search won't be an option. It'll effectively be a linear search in the end because we lose the ability to throw away roughly half the nodes every time we go left or right. Because we always, in that example we had, we always got to go to the right. So I'm gonna have a quick look here to see if I've got some nice slides that talk about the rotations, because they're pretty cool. Does it get slightly worse for every unbalancedness past one? It does, but really, it doesn't need to be so balanced, because on average, it's going to be, so unbalanced trees are basically an efficiency cost. Yeah, you will lose some efficiency, and the most optimal one is going to be if it's perfectly balanced. But for the, like, even if things are a little out of balance and you're not in real big trouble, it's still going to work reasonably fine. But it's as you move further and further and further away from the balancedness, that's when you're moving further and further away from how efficient these operations might be. And you will actually learn a lot more about this next year, because the next set of slides I have are about use an array and perform a binary search when you want to add or remove, find stuff. Well, Cole, you raised some really good question. And these are things, well, you know, I'm not going to answer it right now, but the next set of slides, we're going to learn about a couple of things that will touch what you're thinking. Wouldn't it be easy to use an array and perform a binary search when we just add or remove? Yeah. So, but also remember with an array, you might have to move all the things around and make room for places, make room for stuff if you need to like insert here. But anyways, I was answering another question. Yeah, it gets worse. Yeah, as you move further away from unbalanced, it does become problematic. It gets worse and worse and worse. Okay, the next set of slides that we're going to go over are going to be talking about some sorting algorithms. And I know you might think sorting algorithms are fantastic for teaching concepts in computer science because sorting is a problem, and there are a variety of algorithms that we can look at that sort. Some are good, some are bad, some are way better than others, some are the same as others and whatnot. But we like sorting because it's a well understood problem. Everyone here has at some point in their life had to sort something. It's accessible. We understand that problem. And it's kind of neat to play around and think, well, how, like, you know, we've all sorted things before, but let's come up with like a nice, formal, well-defined set of instructions that works for sorting. Yeah. But before we move on to the sorting, let me know if you have other questions. I will, though, keep looking. Do I have my nice... No, but I could probably find some nice... AVL. I'm going to see if I can find an example in a nice image. See if this will take me to the web page. Okay. Okay. All right, perfect. I found a nice website called geeksforgeeks.com. And there. Okay, so it does look like, yeah, that example I showed would have been balanced. So this is a balanced tree, because I guess the left and right subtrees are no different, are no more different than 1. So the above tree is AVL because differences between heights of left and right subtrees for every node is less than or equal to 1. Okay, this is not balanced. Okay, what is an AVL tree? Blah, blah, blah. Oh no, come on, have better. Okay, insertion examples. So here, if we want to insert 14, where would it go? Well, it would go here. And it looks like the balancedness is going to be maintained. But then, what do we have here? If we want to insert the number 3, I guess we don't have the 14 there anymore, which is fine. If we want to insert the number 3, it would have to go here, right? And suddenly, now we've got a problem, because the heights between this left and right subtrees are different. So what we will do is something called a rotation. In this one, this is called a right rotation. Basically, you are taking this. This is an AVL tree, not a red-black tree. Red-black trees, I'm not as familiar with. And I learned them a while ago, and it's been a while. Basically, what we're doing is, so, where the heck is my mouse? There we go. Okay, so see how it goes 13 to the 10. Well, what we're going to do is basically move the 5 up here, move the 10 down such that it becomes 5's right subtree, because if 5 is to the left of 10, I know 10 is bigger than 5, so it can go in the right subtree. But then we've got this lost little poor 8 here that's going to have to move over to become 10's next one. So we're rotating to the right because the 5 is promoted and the 10 gets demoted, for lack of a better term. And we have to make sure we're being safe with the children of 5. So as you can see, basically, this is what we end up over here. Where the heck? I can't see my mouse. There. The 5 moved up, the 10 moved down. So that is a right rotation. Then, if we insert 45 into this one, here, no. Okay, what do we have? Well, now, let's make this like bigger so maybe I can see, perfect. If we want to insert 45, where is it going to go? Well, it's got to go down here. And then suddenly we are not balanced anymore. So what are we going to do? Well, we're going to do a left rotate. Promote 35. Like, sometimes I like to think about it like, you can't see. Maybe I can do this actually here. So wait, maybe I can do this. Hold on. It's like I grab this and I kind of like lift it up, right? That's always how I kind of visualized it. So grab the 35 and lift it. And then 35 is going to have like 3 children, but that's no good. So we have to take care of the 32 and shove it over to where it would fit. And because 35 is being the new parent, it must be, the 32 must, like, 35's left child must still be on the left of 35. So that's why after, we got to be careful. But I also know that 32, like 35's left child, must also be bigger than the root, the 30, because it's to the right of 30. So it still needs to be to the right of the 30, no matter what happens. Anyways, so I always like to think about it as, geez, this is hard to do. This, there we go. And there, now we have our left rotation. And it's similar for the right rotation when it comes to like the lifting idea that I always kind of had in my head. Nope, not that one. And what do we got here? Let's see. Left rotation, right. Oh, so here's one. This is where it gets complicated. So there's left rotations, right rotations. And then sometimes when you add something and you do something like a left rotation, it creates another imbalancing problem. So you'll have to do a left and then a right. So here we're going okay, the 7 goes here, we got a problem. And if we do a left rotation, we're still unbalanced. So then we have to do another right rotation on the 6 to go up, and the 10 goes down. And similarly, you can have a left and then a right rotation. So there's your more than 30-second little primer on AVL trees. They're pretty cool. You're gonna learn them or red-black trees next year. But yeah, AVL trees, pretty cool. And then the AVL trees can get kind of interesting too. I think it's the AVL trees. Maybe I'm misremembering, but there's another type of tree. No, wait, it's called a threaded tree? Hold on. Threaded binary tree. Yes, that's what they're called. Man, it's been a long time since I took data structures. But there's this really cool idea too, where what you can do is, so if you have binary nodes, okay, and every binary node has a left and right child. But we can have it where they could also have like this like threaded thing where basically if you follow the thread, it'll go to who its successor should be in an in-order list. Or pardon me, in an in-order traversal. So the 1, well, the 3 comes after that. And then the 5 comes after the 3, which is fine because 3 is the right subchild. Wait, am I sharing my screen? Okay, yeah, good. And then, well, the 6 comes after the 5. So this is called like a threaded tree, which is kind of cool too. But again, well outside the scope of this course. Neat nonetheless. And then you might learn about something called B trees and B plus trees, which were the bane of my existence. That was one of the few assignments. That was the only assignment in my undergrad when I worked on like the B trees. That was the only assignment in my undergrad that I submitted an assignment that I knew wasn't 100% correct, because the prof provided a number of like testing examples on data, and my algorithm worked on all but one, and I could not figure it out. And that was, and I think I was one of 2 people that actually submitted a reasonably working that version of the assignment. It was so hard. I don't think they've used that assignment since because it was brutal. But anyways, yeah. So, any other questions about that before we jump to some sorting stuff? Sorting's fun. So I'm going to open up the sorting algorithms nonetheless. 162 slides. Sorting. Cool. All right. So now to sorting. Okay. Well, we're going to check out some sorting algorithms, see how the choice of data structures impacts the algorithm, see a little bit about what a heap is, which is pretty cool. So why sorting? Well, it's a classic problem that we take for granted. We've all sorted things before. Turns out a long time, I mean, humans actually were really bad at sorting stuff until not that long ago. Like, good sorting algorithms were only discovered like 60, 70 years ago. So we actually, like, you might think like sorting, whatever, no, all our sorting algorithms sucked before, at least our formal ones. And newer sorting algorithms come up every once in a while, and understanding the simple algorithms will help you become a better computer scientist in general. So these simple algorithms for these understandable problems that we've all faced with, we have all been faced with, it's just good, right? Because you have the understanding of the problem really well, and so you get to really tinker and play with the algorithms. I will say, if we were doing this in person, which sadly we are not, and if we were doing this in person, and last year we didn't even do it in person either, sadly, but what I like to do is do all these sorting algorithms, but with the students. So we'll like sort students by height, so you can see the sorting algorithm in practice. And I like doing it that way too, because not only it's a little more engaging, it's fun to sort humans, and it gets people moving. But it's also important to remember that we can follow these algorithms as humans executing the algorithm. These algorithms aren't strictly for these computers to execute. if I give you pseudocode for a sorting algorithm, you should be able to read it and sort a collection of humans in a real environment. That's a huge thing to remember when we're talking about computer science, is this stuff really is a lot of times independent from what computational system you're using. But anyways, we can't do that this year, sadly, so bear with me. So how many sorting algorithms can there be? Well, there's BOGO sort, bubble sort, shell sort, comb sort, bucket sort, radix sort, insertion sort, selection sort, merge sort, heap sort, quick sort, TIM sort, library sort. And I've basically only listed like 0.1% of all reasonable sorting algorithms. There are so many. Oh, I hear a boop. What do we got? Nope, not that. BOGO sort is best sort. I agree. We will talk about BOGO sort. So, are some algorithms better than the others? Well, yes, absolutely. And the answer is sometimes. And if you go to this link, we can see some actual like fun visualizations of different sorting algorithms. It's not the best thing in the world, but it's kind of neat. So like you can kind of see how like, well, let's run a bubble sort versus insertion sort. I gave bubble sort a bit of a head start, but let's see how this goes. Look, it looks like insertion sort actually beat bubble sort. Except for when it was in reverse order. That's interesting. Well, we can do a play all and see them all go at once. Let's see who finishes everything first. Well, quick kind of sucked, but it looks like heap, merge, and shell work pretty well. Anyways, what do we got here? What are we looking at? Sorting algorithms. They're sorting. Each column represents a different sorting algorithm, and they're sorting these like lines based on length. And these are different conditions. So I'll refresh the page. So it says like, well, what happens if you use this sorting algorithm on something that is completely random? And then what if you try to use this sorting algorithm on something that is nearly already sorted? Or what if something's in reverse order? And what if something has actually a lot of the same values in there? How do these algorithms react in these different scenarios? Do you ever watch those videos on YouTube, visualize, play? Yeah, those weird sounds where it's like, yeah, I've seen those. They're fun. What he's saying is if you go look on YouTube, you can find like a video of a sorting algorithm sorting a giant list of bars that have different heights. But each bar, whenever it's visited by the algorithm, makes like a noise. And it's like pitch is relative to the height of the bar. So it starts off by making like crazy white noise sounding stuff. But as the algorithm gets closer and closer to being like complete, it gets like more uniform. And at the end, it'll be like because they're sorted. So yes, that is what you're referring to, right? Because yeah, you can find those all over YouTube. Yeah. All right. So here's a couple of popular ones. There we go. All right. Bubble sort. This is a simple, actually, you know what? No. We're going to stop for a moment and I'm going to, let's have a little bit of fun with this. I'm going to make, how many of us are in here? 17. Let's say it was 8, 16. 4. I'm going to make 1, 2, 3, 4. I'm going to make 4 breakout rooms. And you're going to be randomly assigned to these rooms. And I want you to talk amongst yourselves. If you have a mic, fantastic. If not, type away. But I want you to talk amongst yourselves and think of, and if you've seen some of these sorting algorithms before and know how they work, well, don't be that guy. But think about, well, okay, I've sorted stuff before in my life. So if I gave you a stack of exams to sort and said, sort these alphabetically, what are you going to do? I'm certain you are capable of doing that task. But while you do that task, you're going to have some sort of systematic strategy you use to sort these things. You're going to follow an algorithm whether you like it or not. So what is that algorithm you would naturally do to sort those exams? So I'm going to create a breakout rooms, and I want you to talk amongst yourselves to think about what those would be. And if you need a moment to think a little bit, yeah, do that. But yeah, I'm going to make the breakout room. This could be some fun. And I guess for those of you watching the YouTube video, there's going to be a very long, awkward silence. So maybe I'll mute my face so it's not as weird. Breakout groups. I'm going to make 4. Should be, yeah, 3 groups of 4 and 1 group with 5. Okay, and go. All right, I'll see you in a minute. Well, I guess it was because it didn't let you switch groups, so I guess it won't. That meant you couldn't even come back to the main group, but whatever, I fixed it. So I'm curious, like, what were some of the sorting algorithms people came up with? And if you're trying to show off because you already know some of the sorts well, I don't want those ones. I want like what do people do? Look at the first letter, then the second. Well, yeah, I mean you're telling me what an order is, like how an order would be defined alphabetically, but you're not really telling me how you would go and sort the papers. Yeah, I'll sort by first, but you're telling me the ordering, not how to sort the things to get to that ordering. Then take those groups. Oh, sort by, oh, you mean put everything into like an A pile and then everything into B pile. Ah, I got you. Well, actually, I had jumped ahead to, okay, why is this here? Display cap. I'm confused. What is this? All right, whatever. That's actually a really good sort, and that's exactly how I would do. Nope, wrong way. That's how I would sort exams. What I would do is that. And if we want to talk a little bit about the analysis, like if I have n things that need to be sorted, but maybe I don't really care that they're sorted perfectly though. But in your case, like you're sorting the little like subcategories, the little buckets, if you will, which is fine. But let's say I don't really care if they're sorted perfectly. Like if I've got 150 exams and I'm sorting them alphabetically for easy access and indexing in the future. But if someone comes to me and their last name starts with like an M, I could just jump to the M's and then do a quick little linear search in there because whatever, it's sorted enough. But the idea is, if I have n things to be sorted, I'll create k buckets, where in the case of exams, I'm going to do it alphabetically. I'm going to create a bucket for each letter. And then what I'm going to do is I'm going to look at each of the n things and put them into the bucket, the relevant bucket. And the total computational complexity of this is going to be n times k, because I'm going to have to take each thing and compare that one thing to each of the k buckets. And I go, okay, it's an A. Is it an A, B, C, D? Oh, and put it in the right thing. Now, a lot of times, k will be some like fixed number. Like if I'm doing alphabetically, like k is 26, which is of course is just a coefficient. So, it's constant time. We don't care about that. And usually k is going to be much smaller than n, but bucket sort is fantastic for that. But bucket sort has a lot of drawbacks in that, like, well, it won't sort things perfectly. And sure, you could do a bucket sort inside, but then as soon as you start doing like bucket sorts all the way down, that's where you start to lose some of the awesome speed value of like the bucket sort. And the last sort I guess I'll talk about today is going to be BOGO sort. Only because we're running, like, we won't have time to get into any of the good ones, but BOGO sort. Here's an idea. Well, some collection of things is not sorted. So imagine I gave you 150 exams, and I ask you, is this collection sorted? Where the collection is the number of exams. If it's not, shuffle them. And then check again. Is it sorted? If it is not, shuffle again. Is it sorted? If it's not, shuffle again. Do you think this is a good sorting algorithm? If you're having a hard time understanding what I mean, basically, yes, you do. All right, well, we know Alex likes BOGO sort. He already said that earlier. Phenomenal. It is, yeah, everyone loves it. Okay. I mean, kind of order infinity. I mean, we could talk a little bit of a probability, but at the end of the day, I mean, it's possible that I sort the exams and then sort them again, and they actually come up in the same number. It's I mean, very, very, very unlikely, but I could, imagine I took a deck of cards and shuffled them. Imagine I took a brand new deck of cards that was already ordered, okay? And I shuffle them for 5 minutes. It is possible that when I'm done shuffling, they're still in the perfect order. And it's possible that I can do it again and they'll still be in order, and do it again and they'll still be in order. That's possible. It's possible to do a shuffle and have the same order every time. That's possible. Unlikely when n is very large, of course, but it's possible. So this kind of does have like, it's unbounded. Like there is, I mean, it's kind of hard to ask the question of this because really it's just like, it's random. Just chunk everything on the floor and pick them up and hope for the best. That's, well, if you've ever seen me sort exams, mean of that distribution. Well, the distribution's not going to be pretty at all because it's not even like, if everything has, it's going to be a uniform distribution, right? Because every permutation, every ordering of those exams is going to have an equal likelihood, right? So, I mean, it's crap. That's not a good sorting algorithm. It could run forever. And have you ever, okay, if you've ever looked this up, how many permutations a deck of cards? There are 52 decks in each card, meaning that the total possible combination would equal 52 factorial. And if you're wondering why 52 factorial, well, if you consider how many possible orderings there are, pick your first card, an arbitrary card. Okay, I picked it. Now I need to have a card that comes after it. How many cards are remaining? Well, if this is my first card, I have 51 remaining. So first I'm going to pick one of the 52. Then I'm going to pick the 50, then like one of 51, then one of 50, and then one of 49, and so on, and so on, and so on, and so on, and so on. So it's going to be 50 times 51 times 50 times 49, so on, and so on, and so on. So it's going to be 8 times 10 to the 67. That's how many different orderings there are of 52 cards. That's a lot. That's insane. Would the computer not hold enough numbers to do enough random permutations to get the right one? Wouldn't the computer not hold enough numbers to do enough? Well, the computer could hold, as long as it's not remembering each ordering that it did, because all it needs to do is remember 52 cards and then check if they're in order, right? So unless we're like storing them, like if we wanted to store each of the 8 times 10 to the 67 permutations, well, we're going to have a bit of a difficulty there because of how these computers work. I mean, one could build a computer that can do that, but you know, that's crazy. Point being, BOGO sort sucks. Anyways, we'll end here. I'll see you all next Tuesday, and try your best to have a great weekend. Don't work too hard. Rest, 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 rest.